write two quick results about the eigenvectors of normal operators. And by the way, remember that normal includes self-adjoint. So these apply equally well to self-adjoint. Every self-adjoint operator, every normal operator is no, I said that wrong. Every self-adjoint operator is normal because every operator commutes with itself. Okay, so an operator is, so suppose we've got an operator that's normal and a non-zero vector that's going to be our eigenvector. So then V is an eigenvector of T if and only if it's an eigenvector for T star with the eigenvalue being the conjugate of whatever it was for T. Okay, and so the proof of this is pretty quick. First off, notice that if T is normal, this implies that T minus lambda I is normal, right? And so this comes from what we said earlier about how the adjoint of Q minus lambda I is T star minus conjugate lambda I. Okay, so then we have that T minus lambda I applied to V in magnitude is equal to, well, by previous theorem, we can put a star in here and it's going to stay the same. And then by what I just said, we can pass the star inside the parentheses and it becomes T star minus lambda conjugate I against V. So from this, you can see that the null space of T minus lambda I is equal to the null space of T star minus lambda conjugate I, because one side of this equality is equal to 0 if and only if the other side of the equality is equal to 0. And so that's it. So that tells us that the eigenvectors coincide. So then we have sort of the real lead up to the spectral theorem. This is the guts, the glory, and the juice of what makes it work. If we have a normal operator, then the eigenvectors for distinct eigenvalues are orthogonal. And the significance of this is that if you have a normal operator, that will give us an orthonormal basis of eigenvectors. So we've come a long way with our bases, right? So in the beginning, there was a basis, and we talked about bases. And then we talked about whether or not you can find a basis of eigenvectors, and that condition is called diagonalizability. And then we talked about whether or not you can find an orthonormal basis. And we said, oh yeah, by Gram-Schmidt, you can always come up with an orthonormal basis. And then we said, can you come up with an orthonormal basis that gives you an upper triangular matrix? And the answer is yes, and that was Schur's theorem. And now the question is, can you come up with an orthonormal basis of eigenvectors? So this is equivalent to saying an orthonormal basis with respect to which the matrix is diagonal. And the answer is, you can if your operator is normal. That's the spectral theorem, and that's what we'll get to in 7b. And once you've got a basis that's orthonormal and consisting of eigenvectors of an operator, you can use it to solve problems about that operator in ways that would never otherwise be possible. So that's why it's cool. So let's see. So suppose that we've got a couple of eigenvectors. So we're going to take u and v to be non-zero vectors, and we're going to say that tu is alpha u and tv is beta v. Okay, so we've got some eigen data, some eigen junk. Then let's see. So by what we just saw above, T star applied to V is going to be beta conjugate times V. By 721. So let's see what we got. Well, if we do alpha minus beta, so that's some scalar, times the inner product of U and V, this is the same thing as alpha UV minus beta UV, which is alpha U against V minus U against beta conjugate V. And then the first one is TU against V. And the second one is U against T star V. So then using the definition of the adjoint, we just pull the T over to the other side again, well, the T star over as a T, and then that's clearly equal to 0. And so then the conclusion then is that either A minus B equals 0 or U and V are orthogonal. And so if we take the eigenvalues to be distinct, then we know that the eigenvectors have to be orthogonal.